Yeah, so I think the recording has started. Yeah. So
Okay,
yes.
so let me just start. So welcome everyone. Thank you for joining us in on Friday evening, Friday night. So last week we covered some basic topologies, including like homology, cohomology, and so this week Kishore is going to move on to the topological quant codes. So let me hand it over to Kishore. Right.
Yeah.
Okay.
Yeah. So thanks everyone for joining, and definitely I mean it has been getting I would say more technical. So thanks for bearing with me. And I think next week onward we will switch sessions, like the switch gear and move towards subsystem code. Uh, so hopefully, I mean, those of us, like who could not follow, maybe they can again restart. Meanwhile, building on, the topology that we discussed last week, such as homology and cohomology, basically Jet2 homology and cohomology, we will look at its applications. And I have tried to keep a small number of slides so that it's easy to follow. Earlier, I had also thought that, like maybe I will also cover bounds, like quantum error correcting bounds. But I thought maybe that will be too much. And bounds will be covered, like when we will discuss LDPC codes, I think some point in November. So at that point, we will discuss about quantum error correcting bounds, like what kind of codes are possible and not possible, and then like uh, discuss LDPC codes after that. Okay, so let's do a recap of what we discussed last week. So we had this notion of Euler characteristic, which is vertices minus edges plus faces. And when you do that, for example, let's say you do it for a tetrahedron, you get a number 2. You do it for a cube, it has 8 vertices, 12 edges, 6 faces, and you again get 2. And then you see that, for a bunch of different objects, you get 2. Even if you do it for a sphere in a manner that we discussed last week, you get 2. But when you do it for torus, you get a different number. I think you get 0, and so on. So this number is quite interesting, and it's called Euler characteristic. And it can be also written as alternating sum of Betti numbers, where Bn is nth Betti number. So we discussed all this last week. And we say that two objects are topologically equivalent. When we say that, we mean equivalent up to homeomorphism. And by homeomorphism, basically, we mean it's a mapping between two objects uh, that is continuous in the forward direction, continuous in the backward direction, and also bijective, like 1, 1 on 2. So we discussed all this. And then we also talked about, this notion of cellulation. So an n cell is an n-dimensional object in a cellulation. And we had this notion of 0 cell, which was vertices, 1 cell edges, and 2 cell, which was placates. And then we talked about this notion of 0 chain, where we assign an element of Z2, which is like 0 or 1 to every vertex, like basically every 0 cell. One chain, you assign an element of Z2 to every, like edge. Two chain, assign 0 or 1 to every placate. N chain, assign an element of Z2 to every N cell. So we discussed this last week. Then we had also this notion of, like this boundary operator, which let's say takes some object like this. Let's say here, like we had this object. And then it gives its boundary, which is, like, which is boundary. So it's basically, it takes some object, let's say delta n is a map from Cn to Cn minus 1. Like that's what we looked at. So for give every whatever n cell, like sorry, n chain, it gives you basically the boundary of that n chain. That's what the n boundary operator means. And then for every n, there are three groups that we considered. So one was Cn, which was the domain, Zn, which was the kernel, Bn, which was actually it's a Bn minus 1, but you can think of delta n plus 1. So Bn, which is the subgroup of n boundaries. And then we had this relation between these three groups, Cn, Zn, and Bn. And we said that not all chains are cycles, but all cycles are chains. And similarly, not all boundaries are cycles, but all cycles are boundaries. Sorry, not all boundaries are uh, not all cycles are boundaries, but all boundaries are cycles. Yeah. So you see, I mean, okay, in language, when you say, like there can be confusion, but mathematically, what I mean is that Bn is a subset of Zn is a subset of Cn. Okay, it's much more clear in this way. And then we talked about, like this group, homology group, which was the quotient, Zn quotient Pn. And rank of this homology group, basically, as nth number, is the Betti number, which was rank of Zn minus rank of Bn. And this beta n, they are used to define, the Betti number, and they using them in an alternating sum, you can calculate the Euler characteristic. Okay. And then after talking about homology, we talked about this fundamental lemma of homology, which says that boundary of boundary is null chain. That's how you remember. And keep in mind, this we will use quite often today. Like, this lemma, fundamental lemma of homology, we will use quite often. And then we talked about, the analogous notion in the cohomology case, which were like n co-boundary map, and then the group of co-cycles, the group of co-chain, the group of co-cycles, and then the group of co-boundaries. And then you had the nth cohomology group, similar to the nth homology group. Notice that, like here you have, here in the subscript, here you have it in the superscript, in terms of notation. And basically the boundary operator and the co-boundary operator map, boundary and co-boundary map, they are related via this relation. Okay. So I hope all this makes sense. This was all a summary of what we had discussed last week. So building on this, let's try to study topological quantum codes. This will be our focus today. I will try to go as slow as possible to make it more approachable. So let's look at topological quantum codes. So the first thing is that we want to recast Toric code in homological terms. So we looked at homology and cohomology. Actually, we had looked at the applications also of homology and cohomology last time, but we did not recast, let's say, Toric code, for example, in homological terms. So let's just do it straightforward. So recall that in a Toric code, you have, vertices. So these are your vertices of the. So it's a L cross L grid where you have periodic boundary conditions. So these and these, you identify. And these you identify. So it's becomes like this, then a torus. So it's a torus exactly. And then these are called edges. These are called vertices. And these are called placates, like faces. And qubits are placed at edges. Actually, they are placed at the point where you have intersection of a lattice and the dual lattice. Like you see right here, the dual lattices are drawn, and this is where you place it. And we had also studied that there is this notion of placate operator, which is, like corresponding to a face, which is this tensor product of Z operators. And we had also this vertex operator here, like that we had looked at. Okay. So edges that we have, they are they correspond to one cells. I mean, let's say in the homological language, vertices, they are zero cells. Placates are two cells, like in homological. I mean, that's what we will call it. In the dual lattice, you have four cells. Dual lattice placates, they are called zero cocell. Dual lattice edges, they are called one cocells, and dual lattice vertices are called two cocells. This makes sense because vertex in the primal lattice becomes a face in the dual lattice, and then edges get mapped to edges, and then faces get mapped to vertices. And that's how you can see that vertices here are zero cell, but then here zero cell co-cell is a face. You see that the placates are zero co-cell. On the other edges, there are like zero one cell, but there it's also one co-cell. Like you see, one co-cell is edge and one cell is edge here also. Faces we have as two cell. Faces are the placates are two cells, but the vertices here are two co-cells. So dual vertices are two co-cells. So I hope like you see. So qubits. What is a qubit in this language? It's basically it's an intersection point of a cell and one cell and one co-cell. Basically, where we are saying qubits were placed at edges, actually they were placed at the intersection of edges and the dual edges, like the edges of the dual lattice. That's what you're placing. So in this language, you say qubits are basically the qubit correspond to every one cell and every co-cell that intersects it. Okay, so that's where you have qubits. Then you can take tensor product of poly Z operators, and that will be some one chain. So there is some Z operators like at different points. Let's say here, for example, and corresponding to that, you can define like you can take any structure. It need not be like it's like Z tensor Z corresponding to some chain you can allow. And then tensor product of poly X operators, you associate that to one cochains. Okay. So a Z chain operator basically, so corresponding to what was a one chain? One chain was basically assignment of 0, 1 to every like one-dimensional object on your lattice. So a chain was basically to every edge you assign 0 or 1. So your bunch of assignment corresponding to like edge, like you either call it 0 or 1. And for every such assignment, you get a chain, one chain. And now what you can do that you can use this assignment to define tensor product of Z operators. So wherever you assign 0, that becomes identity. And wherever you assigned 1, there is a Z operator. So it's like Z tensor I, tensor I, tensor Z, whatever. Like you assign some 0 or 1, and accordingly, there will be some Z chain operator that you will get. So you get a chain, and that gives you a Z chain operator. So I hope that makes sense. Similarly, you can take some cochain tilde, and it's basically assignment of 0, 1 to every dual edge, which is basically like just edge on the dual lattice. And for a square lattices, it does not matter because they are self-dual, so it's not that complicated. So again, you have your some one cochain, and which is basically to every one dimensional, object, every one cochain object that you have there, it's basically nothing but assignment of 0 and 1 to the edges there. And when you assign 0, it means it's identity there. And when you assign 1, it means it's x there. So you have a bunch of, x tensor, I tensor, x tensor, I, this kind of object. So in this way, basically we can get like, Z operators and X operator. And Z operators are basically coming from chains, and X operators are coming from one cochains, like chains and one cochains here. I mean, in general, for general chains also you can define, but I was just talking about here for one chain and one cochain. Yeah. Okay. So yeah, so you see, at this point we know whenever I put some string like this, you can and let's say, so I take some string, like, I make this kind of a string, which can be, which like it basically corresponds to, let's say, Z, 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 and everywhere else let's say I just assign 0. So I can have a chain which is a string, but I can have more complicated objects also, like it's like this a string, and then I have, something like this. Then there is some non-trivial object. Like I can create any kind of a chain, right? It's like basically wherever I'm putting the blue line, uh, I am assigning 1 to them, and everywhere else it's assigned 0. And you can play the same object for the dual lattice case. You can play the same game for the dual lattice case, and you can get the X operators. So in this way, uh, we make sense. We get Z operators and X operators. But actually, we don't need to talk about Z and X operators. Later they will become obsolete, and everything we will be talking in terms of, like the properties of these one cells and one co-cells and so on. Okay. So yeah, so this is what I was hinting towards, that which we will see now, that how we will get rid of X and Z very soon. So every n qubit poly operator can be written as alpha X Z. We can write like that. Where alpha can be +1, -1, iota, and minus iota. So let's say you have X Z. It can be either XZ is either ZX or minus ZX, right? Plus ZX or minus ZX. Either they will commute or not commute, depending on what kind of X operator and Z operator you have taken. But if they commute, you should get here +1. And if they don't commute, you should get here -1. But what does it mean to say that here we get -1? If we get here -1, then that means P tilde C is actually equal to 1. And if we want them to commute, then P tilde C, the inner product, P tilde, like inner product between these two objects, that will be 0. So this we studied last time. Basically, the inner product will be either 0 and or 1, and that dependent on what was the overlap between chains and co-chains, like that we looked at last week. And actually, like, if you just put a reminder, yeah, I think I have it added here in the summary, but wherever needed, I will again discuss here. But you can, through this also you can see, or you can go through, like last week's recorded video. So you see that we have to just look at the inner product between C and P tilde, and that can tell us whether the corresponding X and Z operator commute or not commute. So X and Z go to the backstage now, and we have to just now look at everything in terms of, like this homological and cohomological language. So qubit, again to remind, is basically intersection point of one cell and one co-cell. Tensor product of Z operator, that was some chain, Polix operator, one cochain. So now I will be just drawing strings and all that, and look at how much they overlap, not overlap, and based on that I will be calling, whether they commute or not commute, and all this game you can play. I mean, obviously, it will be like, you can go through, like, I would say these recorded videos again and again, and maybe try to do it yourself to convince yourself. But I'm saying it becomes super easy to work with these codes. And that's why you see many people don't explicitly write X and Z and just work with those diagrams. Okay. So what are the stabilizer generators? So stabilizer, like, let's say in the Toric code case, we were, like we were drawing it as, like uh, um, basically, let's say some kind of, like this kind of object, like some boundary. So stabilizer generator associated with the boundaries and co-boundaries of two cells and two co-cells. Like uh, that's what we call. So let's say you take some two cell, which is here, and then you take the Z chain operator, which is boundary of C. So you start with two cell, look at its boundary, which will be one cell, and the corresponding Z operator that you write, I mean, according to the way we defined here, that gives you, the placate generator. Similarly, you can look at a zero co-cell, some zero co-cell P tilde, and then look at, do the same thing. Here we have a boundary. Here you do co-boundary. And then you write the corresponding X cochain X operator that will give you the vertex generator. So you get placate generator and vertex generator in this way. Okay. And yeah, like, I mean, how we define this Z and X operator? I mean, we just discussed, right? So I don't need to remind again, but just in case you can define. So the first simple clip that we will see, that earlier we were saying, like they commute and all that and whatever, but now we can take very complicated cases, and we will see how easy the proof is. Like, it's like just 3 lines. So the vertex generator and like the placate generator, they commute. And why that should hold? Because the commutation relation between them is nothing but the inner product between them. But then I can transfer this delta here, like by the inner product relation that we talked. And then boundary of boundary is a, like a 0. So because this is 0, everything just collapses. So you see the power of, like topology. Like in 2 steps, we just prove. I mean, you can make more complicated, whatever wires, these, that, whatever, and you have to just, like follow the topological argument, and you see. So here we are using the fundamental name of homology, and here we are using basically for this line, we are using, like this relation, that you can take delta from here and you can switch to C, right? So we started with this, but then we said that their commutation relation is nothing but the inner product between the corresponding, like uh, uh, objects, like delta tilde P tilde and delta C, like. And then this is same as, like you push delta here, so it becomes delta C. And because boundary of boundary is a null chain, this is 0. So it's P tilde inner product with 0, which is actually 0. So I hope you can appreciate it when like so this is quite powerful. So we got, like we could prove that, like they are indeed stabilizer generators. Yeah, and here we are talking about a particular lattice, but you can take general lattices, and I mean almost similar kind of argument will follow. Yeah. Okay. So now let's look at logical operators. So I'm saying once you get comfortable with this language, then yeah, like I mean, it becomes one can go very slowly and still prove things. Yeah, which normally takes much more time in regular sessions. So logical operators, these are, so let's recall the logical poly operators. They lie within the centralizer of the code, but are not in the stabilizer and are divided into equivalence classes. So what we had seen that, let's say whenever L is a logical operator, LSJ is also the same logical operator, where SJ is some, let's say, some stabilizer. And all these LSJ, like a set of all such operators, they are basically same logical operator. So what are our stabilizers? So basically they belong in a centralizer of the code, means they commute with every stabilizer. And what are our stabilizers? We just looked at. So stabilizer generators, I mean, they are nothing but they are associated with the boundaries and co-boundaries of two cells and two co-cells. We just looked at it. So the question is, we have to find Z chain, ZC, which commute with every stabilizer generator. Now, since any Z chain will commute with the placate generator because they are also Z operator, it suffices to find Z chains that commute with vertex generators because they are the problematic instances. So that's what we have to just worry about. Now you see very easy, how easy it's to find. So last time we were, like, I mean, we were doing some hand waving, but still it was like, rigorous enough, and we were explaining like what those objects are, those logical operators are. But now topology will help us. So we have to find all those p tilde, like delta tilde p tilde. So basically, so we say, right, I mean, what were the vertex generators? So vertex generator is basically co-boundary of p tilde, and associated corresponding to that you write this x cochain operator, and we want our z chain operator to commute with it. But this is nothing but delta tilde p tilde c inner product equal to 0. I mean, just saw. But then this is nothing but I can take delta tilde and push it to here, like in front of c, p tilde delta c equal to 0, which means it should be delta c equal to 0. So it's a set of one chains with 0 boundary, like which has who's basically, like so basically it's a cycle, like which chains have no boundary. It's a cycle. And last time I had to take, like, I don't know, 10 minutes to explain this, like, all this argument maybe. But now here you see we get this directly. So the set of Z chains which commute with every stabilizer is a set where C is a cycle. Got it? You play the same game for the X case. So for the X case, again, you will look at, like xp tilde z delta c equal to 0. But then you forget about x and z and you write it like this. And then it's basically p tilde delta c equal to 0 is same as delta tilde p tilde equal to 0. So this is 0 if delta tilde p tilde is 0. So if p tilde is a one co-cycle. So it's a cycle on the dual lattice. And it has to be a non-trivial cycle because trivial cycles, they are, I mean, I should write here non-trivial cycles, because trivial cycle they will be, the stabilizers. So then we trivially get, like this is a non-trivial cycle, these are non-trivial cycle, these are non-trivial cycle, these are non-trivial cycle, and they correspond to, like your encoded Z operator and X operator, X logical and Z logical. But here we are working with, like, let's say Toric code. I mean, I can take more complicated, like topology. And then again, you can look at the non-trivial loop, and that corresponds to, like the encoded operators. So this is the power of, like, I mean, the abstraction and how we could, like talk about more general cases without doing much hand waving and so on. So I hope, like, I mean, if you could follow the previous sessions and all, you must be enjoying now, like, I mean, like how powerful this formalism is. So, so basically, and then we also said that, you take a logical operator L and you multiply it with some stabilizer Sj, and it's the same logical operator. And in this case, what it will be nothing but, like you add some boundary operator. And that we had talked last time, right? Whenever you have a chain and you have a chain another, so you have a chain C and another chain which is C plus B, they are in the same equivalence class. And what is boundary? Boundary is nothing but, like stabilizer. Like boundary, like this boundary chain. So basically, we have equivalence under multiplication by stabilizer elements. And stabilizer elements are given by one boundary and one co-boundaries. So we need equivalence up to addition with one boundary and one co-boundary. Like, that's the equivalence we need to like categorize our logical operators. But this is nothing but the definition of homological / cohomological equivalence from last time. So you have this, like group Hn, which is coming from, like Zn / Bn, where Bn was, like all this, the group of boundaries. And let's say you just quotient it out, and that gives you, the homology. So the logical Z operators are identified by the element of the first homology group, and X operators identified with the element of the first cohomology group. And the number of logical X operator and Z operator, that can help you, that gives you number of encoded qubits. So the number of encoded qubits is nothing but the rank of, the first homology group. So you just count, like logical Z operator, logical X operators, and that tells you how many qubits you have. Okay. Distance, on the other hand, is not determined by homology of the code. It depends on the cellulation. So, it's not a topological property. Okay. So, I mean, like, I mean, we are going at a very slow pace, but still, like it's the powerful machinery that's helping us cover, like many things that was taking us, like lot of time, like, in the previous sessions. And maybe I'm thinking maybe in another 10 minutes or something, we will be able to finish today's session most likely, or something. Yeah. So what's next? So now next thing is that error correction detection in this topological language. Okay. So now let's look at, Z type errors. So Z type errors, they will be represented by some Z chain, like, ZC. And when errors happen, when you measure the corresponding stabilizer, so let's say Z error happens, and when you measure the vertex of stabilizer, which corresponds to X, it should not commute. And then only you declare that error has occurred. But what does it mean to not commute? It means say that, let's say the corresponding stabilizer, when you measure it, this inner product should be equal to 1. But this inner product equal to 1 means P tilde delta C equal to 1. You can just move delta here in front of it. So it says that the set of vertices whose outcomes are flipped by Z error ZC are the 0 co-cells P tilde which intersect the boundary of C. So it's at the boundary. So earlier, we were saying that there's some Z operator, and then, like there are vertex operator which are at the boundaries, and they are precisely, like, I mean, they will click and they will tell you, some error has occurred. So on the primal lattice, the error syndrome corresponding to C, the syndrome, like it comes from the set of vertices at its boundary delta C. See, yeah. Okay. So I hope you know, like, I mean, you can you make sense of this, yeah. Okay, so next thing is, you know, like similar thing you can do for the X type errors, and basically you will get, you know, you do the same analysis and you say the syndrome measurement associated with an X of error is the set of basically the placates at the co-boundary of this cochain. So you know, always the operators which are at the boundary, they will click and they will give you, you know, like what error has occurred. Okay. And what is error correction? Error correction is nothing but, you know, there is some error which has occurred. See, so basically your goal is that, let's say this is the error, then your goal is to apply some operator such that this operator plus this operator together, they you know, like they form a boundary, like, sorry, you know, like basically trivial loop. So some operator ZC prime, it will correct some error ZC if C prime equal to C plus B for some boundary B. But what if this is not the case? This will cause a correction failure. And in decoders, you know, like we will see this, you know, like, so overall you want, you know, it to be form a boundary, which is a trivial cycle. Okay. So that's it. We finished it, I think, quite early today. So let's summarize this. So qubit is basically, you know, like every one cell and every one co-cell that intersect it. That's why qubit. Tensor product of poly Z operator, that's one chain. Poly X operator, that's one co-chain. The inner product relation between them, like the P tilde and C, that tells you whether they commute or not commute. And then placate generators, they are associated with a two cell C and defined as the Z chain operator Z delta C. So it start with C, look at its boundary, and then associate the corresponding Z operator. That's placate generator. Similarly, you can define vertex generator. Logical Z operator are basically non-trivial one cycles, and logical X operator basically non-trivial one co-cycles. And basically they are identified by the element of the first homology group and first cohomology group, because there is this equivalence up to you know, like addition with a boundary. And yeah, like you have Z type errors, which you figure out by measuring the vertex stabilizers, because that's what clicks and gives you one, like, let's say in terms of the inner product. The X type of errors, they are detected by measuring the placate stabilizers, because that's what clicks and gives you one, like the inner product. And what if this does not happen? Then this will cause a correction failure. So that's it. I hope, you know, like made all sense. I mean, I believe these things, like, you know, to get very quite well versed with this, maybe you need to again go through the topology session. But then if you look at, I would say in the order, like the Toric code and then topology and then this, then many things will make, you know, like quite a lot of sense. And then you can apply to your research and try to extend it for many different cases, more complicated examples, and so on. So yeah, I think this completes the session. We'll maybe stop the recording.
Kishore, can I ask a question? If